Welcome to the IMSAI channel, where I try to resurrect an old IMSAI 8080 computer. Alright, so I thought the next card we would play with is the clock calendar card. So this is a real-time clock and has battery backup. I don't know how good the battery is going to be after 30 some odd years. But looks like a nice card. Looks like it's in perfect shape, so I expect it to do something. I do have the manual, so it gives some sample programs written in BASIC, and so we should be able to go write a little BASIC program, and it should print out the time. Let's see if it works. I'll do the pink pearl on the connectors and put it in the system, and maybe we can try to use the front panel to see if we could even find the addresses and see if the ports are active, and then we'll try a BASIC program. All right, put the card on the extender card, and let's see if we can boot into CPM. That's good. Well, we need to figure out what address this thing is sitting at. The basic program in the user's manual has the addresses at 129 and 130. And that's decimal. Which is interesting. Let's see if we can't find it here at the front panel. So I'm gonna ignore CPM for a while, and let's do a reset. And let's see, 128 is, let's see, so 255 is at this address, so we're looking at 255, and 128 would be this address. Oh, we see something interesting. Oh, wait, we need to do an input instruction. We need to do an input instruction. So this isn't helping. This is not helping. So let's write a program, and we will do an input from FF. We're going to read the switches. And then we're going to do an input how do we do this? Oh, I think we're better off doing this in probably doing this easier in the basic program. I want to do some inputs. So we could well, here, let's do it again. Alright, so reset. Okay, we're going to do an input from, it says 129 and 130. So this would be 128. This would be 129. So let's do that. And then we will output to FF. And jump. There we go. Okay, let's single step this program. Input. We're going to do 29, and we're going to read that, and we're going to output it to FF, and we get 0. Oh, there we go. No, we don't. We get a bit. Let's run this. And we're just getting 1 bit. Okay, so let's look at 130. Oops, 130. Input from 130 and output that. And we're getting the same thing. So either the addresses aren't quite right, and there is a switch here on the front. So let's read the manual, figure out what the switch means. It's probably the address of the card, and then we'll know where to go look. Let's do that first. Okay, I found the page where it talks about the jumpers, or the switches, and it gives, there's six switches, and it tells you if you have all the switches set, then the address is 128 to 131. And I believe we have all of the switches closed. So it says switches on. So we should be here at that right address. Now I think you actually have to command the clock to do something before it will read back. So I think the best bet from now is let's go ahead and load in this little basic program and see if we can talk to the chip. So, yep, let's load CPM. All right. Let's run basic. Okay. They're going to use C1 as one of the ports and C2 as the other port. And there's going to be multiple 4-bit registers. So the output instruction is talking to a port. So we're going to write a byte to the port. So we're going to write the value 16 to port 129. And then okay, so we're going to step through some things backwards. We're going to do another command, this time to the C1 port, which is 130. And we're going to output our D values. And then we're going to grab those 4-bit values, input from C1 this time, 80, I equals I plus 1, next D. Okay, so done with that. T0. All right, then we get to some formatting here. We're at 100, 110. If B is greater than 7, then we're going to put in a space. If T is greater than 7, then T equals t. Okay. So if it's bigger than 7, they're going to shift it down, basically. 130, b less than 8, and t 0 greater than 3, then p equals pm. Okay, 140 if t0, oops, 140 greater than 3, oops, well, I lost track here, 130, 140, 140, okay, if b less than 8 and t0 is less than 4, then he is am. 50 if t greater than 3, then t equals t minus 4, 60, print. The time is t0, t1, colon, t2, t3, colon, t4, t5, AM or PM. 170 out. C2. So I'm going to write 0 to C2 and okay. All right. Save time. Don't want to type that in again. Run. Run. Ooh, it's incrementing. Wow. Looks funny. It's writing the ASCII codes, not the ASCII characters. So it must be written for a different basic. So let's see if the output command. So we're outputting T0. So if we do a print T0, we're getting the actually ASCII. So if we do a print character string of T0, we're getting a blank. And what do we get? We got something like 35. Let's try 35. Print character string T0. Oops. Let's say 35. 35. That's a pound. 31, 35, 36, 37, 40. Yeah, these are not the right values. Huh. But we are
incrementing. So the clock is doing a thing. 38, 40, 41, 33. Went from 41 down to 33. Yeah, so it's within the ASCII range. So ASCII 41. Oops, print. Is parentheses. Let's see. Where is my cheat sheet card? I had it. Here it is. So let's look at ASCII values. ASCII values 1, 0 through 9 are 30 hex. Hex. 30 hex through 39. 41. So I need decimal values. Print hex 29. 29, yeah, it's not quite right. Hmm. Let me make sure the program is right. 30, 37 to 32. I'm going to input b equals t. B is greater than 7. B is less than it's minus 8. If b and b 0, 3, 4. Is it doing AM PM at the end? No, it's not. How come it's not printing AM or PM? Huh. Print P star. So, what is B? 43. So, B, I have a typo. Don't I? No, B. So B is greater than 43. So, yeah, this program's not going to work. B is T0. Oops. I can't type. Print B, print T0. 31 and 41. So 31B, if B is greater than 7, then P, oh, I see. Oh, so P just got set to space. If T is greater than 7, yeah, there's something wrong with this. Let me dig through this and get back with you. Okay, I think I've got some easier program here. So this program, we're going to be looking at just at the 130 register. And inside of the chip, there are multiple registers. And the registers inside the chip, oops, I just flipped the page here on the manual. Okay. So register 32 through 44. So if we send it a 33 command, as we're doing here, we want to talk to the 33 register. Let's start with the 32 register. That's the bottom register. Okay. 32 register is the ones units of the seconds. Then 33 is the tens units of seconds. 34 is the ones units of minutes. 35 is the tens units of minutes, and so on. And you have day of the week and month and year and date and all that stuff. So if we run this, we are going through the ones digits of the seconds registers. So it's going to be counting from 0 through 9 over and over and over again. And the program has the value, the line number 40. If the old value and the new value are the same, it doesn't do anything. So it waits for the digit to change. And then when the digit changes, it prints it out. There seems to be a 32. There seems to be a bit set all the time. So I just subtract 32 and that works. So you can see that we're getting data out every second because it's counting by seconds. If we change line 20 to 33, now we're going to be looking at the tens of seconds. So this would be 30 something seconds, 40 something seconds. So every 10 seconds, this one's going to change. So it counts up to 50 and then it goes back to 0 because 59 would be the largest value you can have in seconds. And then it goes back to 0. So I think we can go back to our original program and we'll know what's going on. Let me save this one. Single, let's see, I'll just call it time digit. Okay, let's load, what did I call it? I don't remember. Was it time? Yeah. All right. So I think this all worked out okay, except um, all of our values need to have a 32 subtracted from it. Or maybe not, 28, 32, 0, 0. I don't know why they're getting a 28. Hmm, that would be, maybe it's a blank. Yes, you see that last digit went from 33 to 44, so it went from 1 to 2. Yeah. All right. Well, we need to subtract 31, at least for a start. Let's see. When we read the data, we're putting it into T1. So let's put the minus 32 right there. So 70. So list 70. We're going to say Ti equals input, oops, C1 minus 32. Okay, there we go. 59. Ah, there we go. This is looking good. So 175, go to 30. Cool. So I guess the next step would be to learn how to program the correct time into it, and see if it can remember it. Um, I'm not sure how good that backup battery is in this thing. It is a bit old. This thing's going to outlast a long time though. Let's let it count up to 59 here and see if it rolls over to 10 minutes. There we go. Perfect. So we have our real-time clock running. Nice. Make sure I save this one.